Now let's see the various notations for a circle. Now that we have seen the equation of a circle in general form, now we have notations through which we understand the circle in various ways. So for example, the general equation of a circle is taken as x squared plus y squared plus 2gx plus 2fy plus c equal to 0. And this equation, which is the general form of representing equation of circle, is usually denoted with s identically equal to this. So this is the notation. When I say s equal to 0, it is understood as the general equation of circle x squared plus y squared plus 2gx plus 2fy plus c equal to 0. So from this, we have various other notations. Say if I just wanted to have S1, the S1 is generally denoted by x1 plus y1 plus g times of x plus x1 plus f times of y plus y1 plus c equal to 0. So this is how we denote for S1. And remember here, x1, y1 is a point. For the point x1 comma y1, we have S1 equals this. Say for example, if I wanted to find S2, then in this case I have x2 plus y2 plus g times of x plus x2 plus f times y plus y2 plus c equal to 0. This is for the corresponding point x2 comma y2 through which I have S2. Therefore, if I have, say, a general point xi, yi, then in this case my Si would simply be xxi plus yyi and so on and so forth. So therefore my Si is xxi plus yyi plus g times of x plus xi plus f times of y plus yi plus c equal to 0. This is how we represent for the point xi, yi. For the point p xi, yi, I have Si is xxi plus yyi g times plus f times plus c equal to 0, where I is anything running from 1, 2, 3, so on and so forth till n. This is how we understand the notation for Si, S1, S2, so on and so forth till Si for the general equation of circle S equal to 0. Now we have the other types of notations. Say if I have the points x1, y1 and x2, y2 as 2 points for the circle, then my S11 or S12 is defined as x1, x2 plus y1, y2 plus g times of x plus x1 plus f times of y plus x1 plus x2 plus f times y1 plus y2 plus c equal to 0 is how we define for S12. Similarly, if I wanted to find S11, then this would be x1 squared plus y1 squared plus 2gx1 2fy1 plus c equal to 0. And S22 is nothing but x2 squared. It is nothing but substituting of x2 and y2 in place of x and y plus y2 squared plus 2gx2 2fy2 plus c equal to 0 is how I just have for the given equation. So this is how we have various notations for S1, S2, Si, S11, S12, S22, etc. So these are the various types of notations which we need to understand, because when we come across many topics in the future, we need to utilize these formulae in application of various concepts. Now let's take an example problem to understand the notations more better. Say for example, I have a problem where I had to find S1 with respect to the point minus 2, 3 for the circle x squared plus y squared plus 2x minus 3y plus 1 equal to 0. So for this circle with the equation given out here, I need to find S1, where the only information given out here is the point minus 2, 3. So now that we have seen the notation, let's initially take the circle denoted in general form as S. As we all know that general equation of circle is represented by S equals x squared plus y squared plus 2x minus 3y plus 1 equal to 0. So in this case, my point here is minus 2, 3, where my x coordinate is denoted by x1 and this corresponds to y1. So with this basic x coordinate being x1 and y coordinate being y1, my S1 is nothing but x1 plus y1 plus 1 times of x plus x1, because 2g reduces to g, as we can see. Now g is 1, so 1 times of x plus x1, and this reduces to 3 by 2 of y plus y1 plus 1 equals 0. So it is very important that 2g becomes g and 2f becomes f, that is half of the coefficient of y and half of the coefficient of x, which comes out here. So half of coefficient of x, which is 2, is 1, so 1 comes here, and half of coefficient of y, which is minus 3 by 2, comes out here, which is a very important note when we simplify for S1. G times of x plus x1 plus f times of y plus y1, this being 2g and 2f of x and y respectively. So in this case, my x1 is minus 2 and my y1 is 3, which I substitute in this. So therefore, I get this to be x1 plus y1 plus x1 minus 3 by 2 of y plus y1 plus 1 equals 0 is what we get out here. Now this, on further simplification, gives S1 equals minus 2x plus 3y plus x minus 2 and plus minus 3y by 2 and minus 9 by 2. Plus 1. Now this, on further simplification with simplification of x terms, gives us minus 2x plus x is minus x, and 3y minus 3y by 2 is 6y minus 3y. So this is plus 3y by 2, and this is minus 2 plus 1, which is minus 1, and minus 11 by 2. So therefore, this is the required value of S1. So as we can clearly see that the circle, which is a second degree equation, reduces to a linear equation, that is S1. So we can see that clearly S1 is a straight line. So I had to make an important note here that S1 equal to 0 is a linear equation or a straight line for the circle S equal to 0 with respect to the point x1 comma y1 is what we conclude. S1 equal to 0 is a linear equation or a straight line for the circle S equal to 0. So this helps us in understanding that. So any line considered for a circle has some properties connected with s equal to 0 and s1 equal to 0, which we are going to see in the future topics. So therefore, with the various notations, I understand that s equal to 0 is equation of circle and it is of degree 2 or second degree polynomial. Now when I take s1, as we have seen in the previous case, it is a linear equation with degree equal to 1. And when I take s11 equal to 0 or s12 equal to 0, this come under constant term because they give a constant value when you simplify. Gives a constant term whose degree is equal to 0 and etc. is how we understand the learning outcome of the notations s1, s2 or and s2 equal to 0 with all these notations. S1 and S2 are linear equations with degree equal to 1, which is a straight line, and S11 and S12 equal to 0 are constant terms with degree equal to 0. Is how we understand each of this. This is a circle, these two are linear equations, and these two are constant values. Now let's see the position of a point with respect to a circle. Now when I discuss about position of a point, there are three different cases through which we understand the position of a point. The three different cases are that a point can lie inside the circle or on the circle and outside the circle. That is, if I take the three possibilities, one is if this is a circle, the point, if this is the circle s equal to 0, then if the possibility is that the point x1, y1 may lie inside the circle. And next, the second possibility is that for a circle s equal to 0, the point p x1, y1 lies on the circle. Lies on the circle. And the third possibility is that the point P lies outside the circle, s equal to 0. So these are the three cases where a point P lies inside or on the circle or outside the circle. Is how we understand three different cases of position of a point. Now when the position of a point is inside the circle, we say that S11 is less than 0. The property is that when P lies inside, S11 is less than 0. Now when P lies on the circle, we say S11 is equal to 0. And when P lies outside the circle, we say that S11 is greater than 0 for this case. So in each of the cases where P is inside the circle, s equal to 0, then S11 will be negative value. When P is on the circle, S11 is strictly 0. If P is outside the circle, then S11 is strictly positive. Therefore, if I give a point and a circle, if I want to know the position of a point, I can just find the sign of S11, and the sign of S11 will decide the position of the point, whether inside the circle or outside the circle or on the circle. And let's see an example problem to understand the concept more better for finding the position of a point with respect to the circle. So for example, I have a problem which says find the position of the point 1, 2 with respect to the circle x square plus y square plus 6x plus 8y minus 96 equal to 0. Now I have a point 1, 2 and have a circle this. Now I want to find the position of this with respect to the circle. That is, I want to find whether this point lies inside the circle or on the circle or outside the circle. Therefore, it is very essential that I find S11 and then the sign of S11 will decide whether the point lies inside, on or outside the circle. So let's see how we can find for this realistic problem. Now the equation of circle, which we denote with S for the general form, is given as x squared plus y squared plus 6x plus 8y minus 96 equal to 0. And the point is P1, 2, where this is x1 and this is y1. Now for finding the position of the point 1, 2, let me find S11. Now we know that S11 is x1 squared plus y1 squared plus 6x1 plus 8y1 minus 96. So I need to find S11 by substituting here. So this on simplification gives 1 plus 4 plus 6 plus 16 minus 96. So 10, 27 minus 96, that is minus 69. As I clearly see that my S11 is negative value, that is minus 69, therefore S11 equal to minus 69 is less than 0, that is negative. And therefore this decides that for a negative value P lies inside the circle, is interior point. Therefore P1, 2 lies inside, or it is interior point lies inside the circle S equal to 0, is how we conclude. The negative value for S11 decides that the point lies inside the circle. So anytime we find the position, we just find S11 and the sign of S11 will decide for a point lying inside, on or outside the circle. Position of a point with respect to a circle. Now let's discuss the power of a point with respect to the circle. Now power of a point Px1 y1 with respect to the circle S equal to 0 is said to be S11. So power of a point is said to be S11. Now this is very much connected with the position of a point, because position of a point is decided by power of a point. That is, if the power of a point is positive, then the point lies outside the circle. If the power of a point is negative, the point lies inside the circle. If the power of a point is 0, then the point lies on the circle. It is through its power that we decide the point lying inside, on or outside. Power of a point with respect to circle S equal to 0 is S11. Now let's discuss about the most important concept of a circle, that is the tangent. Let's see initially on how a tangent is derived for a circle. Now let's define the tangent for a circle. What is a tangent? Now that we have discussed about secant, let's recap with the secant definition of a circle. Now we have seen that if there is a circle and there is a secant which cuts the circle at P and Q. We know that PQ is the chord and the whole of line PQ is the secant. Now this secant, if as I go towards the circumference of circle, that means as I go towards down, I clearly see that the lengths decrease. The distance between P and Q starts reducing until both P and Q unite to become one unique point. That means as this line moves downwards of the circle, we have the length of the chord which is reducing by each of the units, and as it reduces, ultimately this tends to become, if P tends to Q, then ultimately I get a circle with a line touching the circle at only one point, because here, that is, P becomes equal to Q, and therefore this reduces to one unique point where a line still tries to be on the circle where a line touches the circle. So in this case, I get a secant when a line cuts the circle, but when a line touches the circle, I get a tangent. So we can define the tangent to be a line which touches the circle. So tangent is a line which touches the circle, is how I define the tangent. Any line which touches the circle is called a tangent, and it is derived from a secant where P tends to Q and I get one unique point where the line touches. So when P tends to Q for a secant, I get a tangent. Now let's see some interesting properties for tangent of a circle. Now when I take a circle, I clearly see that there are infinitely many points on the circle, therefore there are infinitely many tangents which I can draw. Etc. So this is how I see that there are infinitely many tangents which I can draw all across the circumference of the circle. Therefore, I can say the first property that infinitely many tangents can be drawn for the circle, is how I understand the tangent property for a circle, because circumference has infinitely many points, therefore every point has a tangent, therefore infinitely many tangents which can be drawn for the circle. Now let's connect the tangent with position of a point. Now that we have discussed about position of a point, let's see how we can connect that with the tangent. Now, as we have seen the three different cases of inside, on and outside, I have three cases where if I take a circle, the point can be inside the circle, and then for this I have the point P lying on the circle, and then for this point P is outside the circle. So therefore, in this case of three different cases of inside, on and outside, let's see how the tangent is connected with position of a point. Now when a point is inside the circle, I cannot draw any tangent through P. That means no tangent can be drawn through P x1 y1. But here, as I clearly see, yes, I can draw one tangent through P. That means when a point is on the circle, there's only one unique tangent which I can draw through P. So here it is one tangent, and now from here, for a point outside P, I can draw two tangents, that is tangent 1 and tangent 2, that is two tangents can be drawn through P x1 y1. One tangent can be drawn through P x1 y1. No tangent can be drawn through P x1 y1, is how I understand the position of a point connected with the tangents. Now let's define the length of the tangent for the circle. So now that we have defined the tangent for a circle, let's see what exactly is the length of tangent we define in the mathematical sense. Now suppose I take a circle S equal to 0. Now for this circle, if I have a point P x1 y1 which is outside, then and if I draw a tangent through P, where this cuts here at A, then in this case the point P x1 y1 through which I draw the tangent makes some length with the circle. So this length from point P to the point of contact of the tangent is called the length of tangent. Now here A is called the point of contact because this is the point where the tangent makes contact with the circle. So A is point of contact, and therefore length of tangent with respect to circle S equal to 0, and if suppose I have this x1 y1 is length of tangent is AP and it is given by root S11 is the formula I have for length of tangent. So length of tangent from the circle is PA and it is root S11. So now that we have discussed about position of a point, similarly we discuss about position of a straight line with respect to the circle, as we have there with three cases with a point lying inside the circle, on the circle or outside the circle. Similarly, a circle has three different cases when we discuss about position of a straight line with respect to the circle S equal to 0. So let's discuss the three cases where a line L cuts the circle S equal to 0, then it cuts making two distinct points P and Q. So one is the possibility that a line cuts the circle, one is the possibility that a line touches the circle, this, and one is the case where a line does not pass through the circle. So when a line cuts the circle, it has 2 points of intersection. When a line touches the circle, it has 1 point of contact, and when a line does not cut the circle, there is no point of intersection. This is how we understand between three cases: case 1 cutting the circle, case 2 touching the circle, and case 3 does not meet the circle. Now let's see what will be the mathematical conditions for each of the three cases where a line cuts the circle, touches the circle, and does not meet the circle. So if I take the radius of the circle as r, and if I take the center of the circle here, then each of the circle with same radius r, then let me say the perpendicular distance from center to the line is P, is small p, and the perpendicular distance from center to the line is P, and the perpendicular distance from center to the line is P. Then I say P is perpendicular distance from center to line L, that is center of the circle to the line L. Now, as I have in three different cases where the perpendicular distance from center to the line is P here, and this P is here, and this P is here, then I see that if the perpendicular distance of this is less than radius, then I get case 1, because clearly I see that the radius is extended till down, but perpendicular distance is only till here, so P is obviously less than R. P less than R. So this is the case for a line cutting the circle at 2 points. Similarly, for here, I have clearly P is equal to the radius because radius itself is the perpendicular distance. So when a line touches the circle, the perpendicular distance is equal to the radius is the case for the second case of line touching a circle. Now as I see that P is greater than the radius which ends only till here, that is the radius is only till here and P is still here. So clearly P is greater than R. Therefore, when P is greater than R, the line does not meet the circle. When P is equal to R, the line meets the circle, and when P is less than R, the line intersects the circle. This is how we understand the three different cases connecting the radius with the perpendicular distance from center to the line. Now let's see the equations of tangents for the circle in various different properties. Now say I have a circle passing through origin and having radius R. That is, equation of this circle is x square plus y square equal to r square, because center is origin and radius is r. So for this circle x square plus y square equal to r square, let me draw a tangent somewhere here. Now let me say this is the tangent for the circle which has slope m. So the tangent has the slope m. Now for a line which is a tangent to the circle with slope m, for the circle x square plus y square equal to r square, equation of tangent is given by the formula y equals mx plus or minus r times root of 1 plus m square. Is how we get. Now plus or minus gives us two tangents, because if I have a tangent here, now when two lines are parallel, the slopes are equal. Therefore, there is another line which is equal, exactly parallel out here. When this is a line which is parallel to this, and therefore this also has slope m. There is a possibility that there are two lines, there are two tangents for a circle which are parallel to each other, this being parallel to this on the other side of the circle, and therefore the slope of this will also be m. Therefore equation of tangent t and t dash will be given by this, one with plus and one with minus. Hence there are two equations out here, one given by plus and one given by minus. So when I have a tangent whose slope is known, then for this circle with center origin and radius r, I can find the equation of tangent where m is slope and r is radius. It's radius of circle, and this is slope of t. This is how we understand the formulae connected with finding equations of tangents. Now let's see the equation of tangent where the circle is not in the standard form. What if the circle is in general form? What if the center of the circle is not origin? Also, we need to derive the equation of tangent. So let's see for a general equation of circle how we can find the equation of tangent respectively. So I have a circle whose equation is given by s equals 0. Now I have a tangent at here whose slope is given to be m. The slope of the tangent is m is what we have. Therefore, equation of tangent t whose slope is m is given by y plus f is equal to m times x plus g plus or minus r root 1 plus m square. Now here r is the radius of circle and f and g we know are from standard equation x square plus y square plus 2gx plus 2fy plus c equal to 0. So r is radius of circle which is given by root of g squared plus f squared minus c. We know this from the formula. And m is slope of tangent t. Is how we understand the formula for equation of tangent with slope m. One is plus, the other on the opposite side is given with t dash. These two lines being parallel has the same slope. So therefore equation of t and t dash are given by this. The two lines parallel to each other and the tangents for the circle S equal to 0 are given by this equals this plus or minus of r times this. R is the radius and m is the slope. Now let's take the concept condition for existence. When do we say that a line is a tangent to the circle or is not a tangent to the circle is the biggest question of the topic. So we need to identify on whether a line is a tangent to the circle or is not a tangent to the circle, which comes under condition for existence. What is the essentiality for a line to be a tangent to the circle? So let's see out here. When I have a circle, when I have a tangent at point P, x1, y1 with the circle equation being S equal to 0 in general form, then we know that the center is minus g minus f from here. Now condition for a line to be a tangent to the circle is that radius must be equal to perpendicular distance from center of circle to the line is what we conclude. If this is equal to this, then we say then the whole of this perpendicular distance will give us the condition. If radius is not equal to this, then the line is not a tangent to the circle. If radius is greater than perpendicular distance, then we say the line is outside the circle, does not meet the circle. If radius is less than perpendicular distance from this, then we say the line is non-intersecting. But if radius is greater than perpendicular distance, then we say the line is intersecting or cuts the circle at 2 points. We have taken this in the previous 3 cases, but now the condition for existence of a tangent is that radius must be equal to perpendicular distance from center of circle to the line T. Now if I take the equation of tangent in general form as ax plus by plus c equal to 0 as the general equation of line this T, then ax plus by plus c, then I have the radius which is given by root of g squared plus f squared minus c. We all know that radius is calculated from the circle S equal to 0, where S is x squared plus y squared plus 2gx plus 2fy plus c equal to 0. Therefore, radius for this circle is root g squared plus f squared minus c, which must be equal to perpendicular distance from center to the line, that is mod ax plus by plus c by root of a square plus b square is how I understand the property of this connected with this. So condition for existence of a tangent to the line is that this must be equal to this, where this is the line and this is the center of the circle for the standard or the general equation of circle being this. Now let's see the condition for existence of a tangent for a standard form of a circle. That is, if I have a circle with center, origin and radius r, then what is the condition for the line y is equal to mx plus c to be a tangent to the circle is what we discuss. So the condition here is that c must be equal to plus or minus r root 1 plus m square, where r is radius of circle and m is slope of line t. Is how we understand the condition for this line to be a tangent to the circle x square plus y square equal to r square, center, origin and radius r. The condition is c equals plus or minus r root 1 plus m square. So if c is equal to this, then we can say that the line y is equal to mx plus c is a tangent to the circle x square plus y square equal to r square. Condition for existence of a tangent to the circle in standard form. So let's see how we can find the equation of secant for the circle. Say for example, I have a circle S equals 0 and here is a secant which cuts at 2 points P x1 y1 and at Q x2 y2. If the line L cuts the circle at points x1 y1 and x2 y2, then this line is called the secant. So we know that PQ is the secant for the circle S equal to 0. Therefore, the formula for equation of secant PQ is given by S1 plus S2 equals S1 2. This is how we understand the equation of secant for the line for the circle S equals 0. Now that we have defined the equation of secant, we will derive for equation of tangent in the similar manner. Now say for example, I have a circle S equal to 0 and I have a tangent T at the point P x1 y1. Then equation of tangent at point of contact P x1 y1 is given by equation of tangent P at P x1 y1 with respect to the circle S equal to 0 is S1 equals 0. So when I want to find equation of tangent at P with respect to the circle S equal to 0, it is S1 equal to 0. We know that S1 is xx1 plus yy1 plus g times x plus x1 plus f times y plus y1. plus c equal to 0 is the equation of tangent for a circle S equal to 0. So if I have a standard form of circle, say a circle with center as origin and radius as r, then the equation of tangent at Px1 y1 for the standard circle x square plus y square equal to r square is given by equation of tangent at P x1 y1 with respect to the circle. This is given by xx1 plus yy1 minus r square equals 0 is how we have. Now this is again derived from S1, because if I assume this to be S, it's again the S1 which we have identified. So S1 equal to 0 is the base of understanding the equation of tangent for the circle S equal to 0. Now let's understand the topic of finding the point of contact. How do we find the point of contact which the line makes with the circle, that is at the point where the tangent meets the circle? So for example, I have the problem which says find the point of contact which the line 4x minus 3y plus 7 equal to 0 makes with the circle x square plus y square minus 6x plus 4y minus 12 equal to 0. So the question here is to find the point of contact which this line is making with this circle. So let's see how we can find the point of contact. So as I clearly see that it is given that the circle is x square plus y square minus 6x plus 4y minus 12 equal to 0, and the tangent line T is given to be 4x minus 3y plus 7 equal to 0. So as I see here, I don't have the point of contact. Because I want to find the point of contact, I say let P x1 y1 be the point of contact of T with S, that is the line T with the circle S. Therefore, if I have a circle S equal to 0 and the tangent T at which the point of contact is Px1 y1, the line is already given to be 4x minus 3y plus 7 equal to 0. Therefore, with the line given, now let's find the equation of tangent for this circle S equal to 0. Now we know that equation of tangent T at Px1 y1 with respect to the circle S equal to 0 is given to be S1 equal to 0, which we know through the formula. So using this S1 equal to 0, that implies we have S, which is xx1 plus yy1 minus half of minus 6, which is minus 3 of x plus x1 plus half of this 2 times y plus y1. This, on further simplification, gives us the equation of tangent in terms of x1, y1. So therefore, continued from there, I have the equation of tangent which reduces to x(x1) plus y(y1) minus 3x minus 3x1 plus 2y plus 2y1 minus 2l equal to 0. This, on further simplification, gives me this and this, when taken with x common, x1 minus 3 of x, and this with y, y1 plus 2 of y, and this, and the constant plus minus 3x1 plus 2y1 minus 2l equal to 0. Now this is equation of tangent t, which is obtained using the formula s equal to 0. But the equation of tangent is already given to be 4x minus 3y plus 7 equal to 0, which is also the equation of the same tangent t. Therefore, these two lines must be same. So if I take this as 1 and equation 2, I clearly understand that 1 and 2 represent the same line t. They represent the same line t. Therefore, their coefficients must be in same ratio. Therefore, x1 minus 3 by 4 must be equal to the y coefficients, which are in same proportion, and the constants minus 3x1 plus 2y1 minus 2l by 7. They should be in same proportion, through which we find x and y. So let's try to find x1 and y1 from these two equations. So as I take these two equations, I have in cross multiplication minus 3x1 plus 9 as 4y1 plus 8. This 3x1 plus 4y1 is 1 when on arranging the terms. Then I have the first and last equation which I take, and then on simplification gives me 7x1 minus 21 is minus 12x1 plus 8y1 minus 48. This, on cross multiplication, gives this equation. Now 12 plus 7, which is 19x1, and minus 8y1 is minus 48 plus 21, 31, 41, which is minus 27. So this I get as equation 1, equation 3 and equation 4, where equation 3 and 4 are solved using the elimination method. So I multiply this equation with 2, and then I get 2 times of 3, which is 6x1 plus 8y1 equals 2. This, on adding, gives me 19 plus 6, which is 25x1 is minus 25. That implies x1 is equal to minus 1. So I get the value of x1 is minus 1, which I substitute here. Therefore, substituting in 3, I get 3 times of minus 1 plus 4y1 equal to 1. That implies 4y1 equals 1 plus 3, which is 4. That implies y1 equals 1. So x1 is equal to minus 1 and y1 is equal to 1. Therefore, the point of contact the required point of contact is P, which is x1, which is -1, and y1, which is 1. So this is the required point of contact, which we find using the concept of S1 equal to 0 and the proportion which gives the values of x1 and y1. The point of contact can be found in this method. Now let's find the equation of chord where the points are given in parametric form. So now that we have considered the topic of parametric form of the points on the circle in the previous session, so let's recap with finding the equation of chord in parametric form. So we know that a parametric form involves the radius and the angle which we consider for the point. So therefore, for the circle S equal to 0, if I have 2 points where a chord is formed, where this is A for θ1 and B, which corresponds to the angle θ2 for the circle with radius r, then we know that θ1 corresponds to the point minus g plus r cos θ1 and minus f plus r sin θ1, and the point B with the angle θ2 corresponds to the point minus g plus r cos θ2 minus f plus r sin θ2, 0 less than or equal to θ1 and θ2 less than or equal to 2 pi. So with these 2 points, I want to find equation of chord, which is given by AB, which is given by x plus g cos θ1 plus θ2 by 2. Then this is y plus f sin θ1 plus θ2 by 2, which is r cos θ1 minus θ2 by 2 is how we understand the equation of chord given by this formula, where the 2 points, the endpoints of the chord, are considered in parametric form as a θ1 and a θ2. So equation of chord is this in parametric form for the circle S equal to 0. Similarly, let's see the equation of tangent in parametric form for the polar coordinates r, theta. Say for example, I have a circle S equals 0, and then I have a tangent T at P theta. So let me say the polar coordinates of the point P, the point of contact of the tangent with the circle, is theta, and let radius of the circle be r. Then with r being the radius of circle and theta being the point of contact, I have p theta, which is given by minus g plus r cos theta minus f plus r sin theta. Therefore, with this point, equation of tangent T at p theta is given by x plus g of cos theta plus y plus f of sine theta equals r, where r is the radius and theta is between 0 and 2 pi. So equation of tangent at theta is given by x plus g cos theta plus y plus f sine theta equals r. Now let's try to find the equation of tangent in standard form. That is, if I have a circle with radius r and center as origin, that is, if the equation of circle is x square plus y square equals r square, then for the point p theta equals minus g plus r and minus f plus this reduces to r cos theta and r sin theta, since g and f are equal to 0, they vanish. Now therefore, for this point r cos theta and r sin theta, equation of tangent t at p theta for the circle x square plus y square equal to r square, equation of tangent at this with respect to the circle x square plus y square equal to r square is given by x cos theta plus y sin theta equals r, is how we understand the equation of tangent at point p theta for the circle x square plus y square equal to r square in standard form. X cos theta plus y sin theta is equal to r in parametric form. So now that we have defined the tangent, similarly we define the normal. The tangent and normal are always associated with each other. Wherever there is a tangent, there is a normal, and wherever there is a normal, there is a tangent for the circle. So let's see what is the normal for the circle. So before we understand the normal, let's recap with the tangent of the circle s equal to 0. So I have a circle s equals 0. So for this circle, let me draw a tangent at P. So this is the tangent at P, x1, y1. So if this is the tangent for the circle, then a line which is perpendicular and passing, any line perpendicular to the tangent and passing through point of contact is the normal. There are infinitely many lines which are perpendicular to the tangent, but there is only one line which is perpendicular to the tangent and passing through P. That is, it passes through this. This is the normal. This is the tangent. So we understand that a line which is perpendicular to the tangent and passing through the point of contact is the normal. So in this case, this is the normal. But there is a very important geometrical property we need to understand, that the normal always passes through center of circle. So normal is perpendicular to tangent and normal passes through center of circle. Because radius is perpendicular to tangent, this being the radius will pass through the center of circle. So we always have n perpendicular to t. This is how we define the normal connected with the tangent and passing through the point of contact. It is very important to note that a normal has a very basic peculiar property, that is, since there are infinitely many lines which are perpendicular to tangent, there exists only one line which passes through the point of contact Px1 y1 and is perpendicular to T. Therefore, I can say with this property that for every tangent there is only one. Therefore, for every tangent there exists one and only one normal, is how we understand this property. So every tangent has only one normal which it passes through. There cannot be two normals for one tangent. So the normal being this perpendicular to and passing through Px1 y1, the point of contact. Uniqueness of the normal of the tangent T. Now let's derive for equation of normal of the circle S equal to 0. So we know that for the circle, the general circle S equal to 0, I have the normal which passes through the point of contact and is perpendicular to tangent. I have to find equation of this line which is the normal. So in order to find equation of this normal, that is the line, I have the formula before which we have the general circle, that is x squared plus y squared plus 2gx plus 2fy plus c equal to 0. Now the point of contact is Px1 y1. Now for this point of contact, my equation of normal n is given as the formula x minus x1 into y1 plus f minus y minus y1 into x1 plus g equals 0. This is the equation of normal at the point Px1 y1, at the point of contact Px1 y1. So equation of normal is given by x minus x1 times y1 plus f minus y minus y1 times x1 plus g equal to 0, where x1 and y1 are obtained from this and f and g are obtained from the general equation of the circle S equal to 0. Now let's derive for equation of normal for standard form of a circle. That is, if the circle has center as origin, that means, and the radius is r, then in that case the circle has the equation in the standard form as x squared plus y squared equal to r squared. So for a circle in standard form, the equation of normal n at Px1 y1 with respect to the circle x squared plus y squared equal to r squared is given by the formula xy1 minus yx1 equals 0, is how we have from the standard form of the circle. xy1 minus yx1 equal to 0 is the equation of the normal. Now let's see the angle between the two tangents for the circle S equal to 0. So how is the angle formed between the tangents is the biggest question out here. So for example, I have a circle S equals 0 and I have a point Px1 y1 outside the circle. Then from this external point, we have already discussed that there are two tangents which can be drawn from a point outside the circle. Therefore, the two pair of tangents are given by one this and this. So the two tangents are T1 and T2, which give the angle. So this angle can be formed using the relation. If this is theta for the circle, then theta is the angle between the tangents T1 and T2, which is given by the relation tan theta by 2 is equal to r by root S11, where r is radius of circle S equal to 0, and p x1 y1 will decide the point this, and theta is given using the relation tan theta by 2 equals r by root S11. Is how we find theta, the angle between two tangents of a circle. Chord of contact for the circle S equal to 0. So what is the chord of contact? As we know that the chord is the part of the circle, the line which cuts the circle into some segment, then we have the chord of contact defined in the similar fashion. Let's see how the chord of contact is defined for a circle. I have a circle S equals 0, and I have an external point P x1 y1 from where I can draw the two tangents T1 and T2, which make the point of contacts as A and B. Now, as we know that from an external point there are two tangents which can be drawn to the circle, that is, there are 2 points of contacts. Those 2 points of contacts just join to form the chord. So this kind of a chord which is formed from an external point being considered with two tangents is called the chord of contact. So this is called chord of contact. And equation of chord of contact at P x1 y1, for P x1 y1 with respect to the circle S equal to 0 is given by S1 equals 0. So the equation of chord of contact is S1 equal to 0, which is obtained from an external point from where the two tangents are drawn. The chord of contact with the equation S1 equals 0. So let's connect the chord of contact with respect to position of a point. Now that we know that the position of a point has 3 cases. One is the point outside the circle, the point on the circle, and the point inside the circle. So if I consider all the 3 cases, case 1, case 2, and case 3, I have the circle from where an external point. For case 1, I have P outside the circle where I get 2 tangents which can be drawn. So I get 2 points of contacts where I can join this. For case 2, where the point is on the circle, I have this on the circle where I have only 1 tangent. Now case 3, where the point is outside the circle, where the point is inside the circle, I do not have any chord of contact. So these three cases gives me the consideration that for an external point AB is the chord of contact, and for the point which lies on the circle, tangent T itself is the chord of contact, because this itself acts as the chord of contact. Now for this, there is no chord of contact through P, no chord of contact of P x1 y1, because P x1 y1 lies inside the circle. Therefore, we get three cases where if P lies inside the circle, there is no chord of contact. If P lies on the circle, the chord of contact is the tangent at that point itself. And if P is outside the circle, the chord AB is the chord of contact of P x1 y1. Is how we understand the chord of contact of each of the positions of P outside, P on, and P inside.